Froggy here, and welcome to Module 5 of our class. Now this module of the class is all about climate models. Climate models are going to be another way in which we can understand the climate system and what changes are happening to the climate system. Kind of part of a pair of lectures, pair of modules that goes together with the one that we learned about observations of the changes in the climate. But we weren't ready to learn about climate modeling at that time. We had to spend some time first on like the physics of climate and so on. I am talking to you today from my basement where my two little boys have their Thomas the Train stuff set up. If Thomas the Train was a religion, my two children would be its high priests. They know everything about everything Thomas. This is the Thomas table where Thomas and his friend, where's Thomas? Here's Thomas. Thomas and his friends have are trains, if you didn't know. They are little trains, and they have little adventures, and they have a TV show, and they have tents and costumes, and oh my goodness, the whole works. And they're models. They're models of trains, in a way. Model is a really interesting word in the sciences. Model, in a very general sense, means a simplified way of understanding something. To represent something real and complicated using something that is simpler. And we use models lots of different ways, and there's lots of different types of models out there that can be used to solve different kinds of problems or to be used to understand different kinds of aspects of the climate system or any other scientific problem. The Thomas models here are an example of a physical model. Now, what we mean by a physical model is I can pick up, who do I have here? They all say their names on the bottom. This is Henry, apparently. Henry here is one of the trains. This is a model. Now, the people who make the Thomas stuff, I mean, there is a real train that this is based on. You know, but I don't know what the backstory of Henry is or whatever. But the real train looks a lot like this. But it's a complicated thing. It's a steam engine. It has thousands of parts, and they move, and they have to be fixed, and all this kind of stuff. Not the best thing to give to the toddler set. So this is a model of Henry, but it's a greatly simplified one. And, I mean, it still has wheels. In fact, I bet the real train that Henry is based on has 8 wheels on its engine, although maybe it doesn't. And it hooks together with railway cars, let's see if I can get it to do it, and pulls through. Now, in the case of Thomas the Trains, it's held together with little magnets. It runs on tracks. It's a type of model. A little kid who has never really seen a real steam engine can take a look at, apparently this is Emily, and learn a lot about steam engines. I mean, like, they go down tracks, and they hook together. Now, the real reason kids are into Thomas type stuff is the cute stories, and they learn fine motor skills and spatial awareness. And actually, the cool tracks that they use it's kind of an interesting, complicated system to put together, and the kids kind of learn spatial skills and problem-solving skills and stuff like that. It is a set. It goes together. Thomas has friends who aren't trains, like Alfie apparently is a backhoe or something like that. And there are skills they're learning when they're playing with this. And these models are telling them something about the real train. This is a little tank engine. It is a little wooden replica of one, but the kid is actually learning something about real trains. If they've never seen a train, this is actually a pretty good place to start. If you were talking to somebody who had never seen a train before, this is not a bad place to start. But if you really haven't ever seen a train before, maybe Thomas trains aren't the best place to start. Maybe you want a more complicated understanding of what a real train is like. For example, maybe the kind of understanding you could get from an HO model railroad. If you're not familiar with HO scale model railroads, they're the kind that you see in the store that are fairly fancy, where the train has lots of little parts that move, and you can be the conductor and you control it using some kind of switch to make the train go and stop. And you can learn more about what real trains are like. The hitches are more realistic. They are all based on real trains, and you can learn about the design of trains in different eras. And you can even learn physical things about how trains work from those models. For example, you might be able to learn something about what it's like when the train goes off a rail, or how fast the train can go around curves,
or what happens when the train tips off, or whatever. And so you could get a more sophisticated understanding of what real trains are like using a different kind of physical model, in this case the fairly fancy HO scale model trains. But no matter how fancy or complicated these models are, whether they're a simple little Thomas train or whether they're a fancy HO scale train that like a collector would have, you know what they're not? A train. They are still just models of trains. They are not real trains, which have thousands of real parts, all of which are necessary and have purposes, and it's all extraordinarily complicated. It takes whole teams of people to keep trains running and to maintain them and to schedule them and load them, and all these systems that are not well represented necessarily by these little simple models. On the other hand, maybe for the purposes of what you're trying to understand about trains, these simple models are enough. If you're just trying to learn the basics of, like, problem solving and spatial recognition, stuff like that, Thomas is a great toy. If you want to learn about, like, maybe the history of design of railroad engines, maybe an HO scale model is exactly what you need. But either way, those are just physical models. They're something you can hold that represents the more complicated system.
But actually, there's several other kinds of models that are helpful for understanding the natural world too, or really any kind of system that you're trying to study from a scientific point of view. For example, there are statistical models. They're near and dear to my heart because one of the classes I teach here at Creighton is in the energy department. I teach modeling electrical load and yield, which is a class about like solar power and wind power under different conditions. And let me show you one of the graphs that the students make in that class. This is using some data that OPPD, the power company in Omaha, gives us. On the x-axis, it's temperature in Omaha, and on the y-axis, it's just the total electrical demand for the city. And they gave us, I don't know, maybe 7 or 8 years of data. So every little blue spot on the graph there corresponds to a time when they could see what was the temperature versus what was the electrical load in Omaha. And you can see that they make kind of a U-shaped pattern to those blue dots, where the colder and colder it gets in the winter, the more electrical demand there is in Omaha. And the warmer and warmer it gets in the summer, once it gets hotter than about 60 or 70 degrees, the more and more electrical demand there is based on how much air conditioning there is using. And the students try to figure out if there's a way to write an equation that describes this. The particular diagram I used on here, they were trying to use a curve to fit, where they were trying to say, okay, if you knew the temperature, what would be a good estimate as to how much power Omaha was going to be using? This is a statistical model. The past observations of the weather and electrical needs in Omaha were used to make a prediction to help us understand what was going on with regard to electrical load. I suppose OPPD, the power company, could make a physical model of Omaha and do the same sort of thing, where they built little houses and they would like heat the little houses and put cold air over them and see how fast they lose heat. But that's not really very effective when you're talking about something, as big and complicated as like a city with thousands and thousands of houses all losing heat at different rates. Just using the past observations, the past performance of what was the city doing, turned out to be a good way so that we could use a statistical model to describe what the electrical needs of the city were going to be.
Yet another type of model we could be talking about is what's called a conceptual model. A conceptual model is sort of like an idea that you have in your head about how things should work. I have a conceptual model, for example, up here of the hydrologic cycle. The hydrologic cycle is how water flows through the Earth, atmosphere, cryosphere, ocean system, and how there's all these processes at work that are transferring water from the ocean to the atmosphere by evaporation, from the atmosphere to the ground by precipitation, from the ground into groundwater by infiltration, and so on. A lot of what we do in science education is actually conceptual models, where we're building this basic idea of how stuff is connected. And it's actually kind of an amazing and a powerful thing, because it helps you wrap your mind around a very complicated system. The real hydrologic cycle is quite a bit more complicated than this, and the rates at which water is being moved from the ocean into the atmosphere, or the amount of water being stored in groundwater. It's all very complicated, but this simple conceptual model kind of helps you wrap your mind around the whole thing.
All these types of models that we've been talking about so far are important, and they were used in different ways in science and engineering and problem solving in general. But none of them are how we come to understand climate using climate models. That's going to be another type of model called a numerical model. And we're going to talk more about numerical models in a few minutes, but I thought I'd start off, take a pause real quick here to look at some questions. Question 1. Suppose I've been gathering measurements of the ages of boys and their heights. I find that overall, the older a child is, the taller he is. And based on that information, I made an equation that predicts the height of the child, just based on the boy's age. Some boys are going to be higher than that, but if they know that you're 4 years, 3 months old, how tall would the average boy be, or something like that. That equation would be described as an example of a blank model. Conceptual, statistical, or physical. Alright, make one of your choices from the list of 3 below here, and get a little feedback before we move on to question 2.